So, welcome to the second seminar of this series that is devoted to discuss trends and research directions on advanced cyber-physical systems. So, as you know, the topic for today is about remote sensing. It will be presented by our colleagues José Fonseca and André Mora. So, they have been working on this topic for several years in different projects. So it's a great pleasure to have them making this presentation today. And after the presentation, there will be also a period for discussion and to ask questions, but also for you to express your opinions, your even complementary points of view. And I asked our colleagues Luis Oliveira and Pedro Pereira to help in the moderating this second part of the discussion period. So we can start now. Then I'll give the floor to José Manuel. I guess you start.
Okay. Yes, thank you. Thank you very much. So first of all, I will share my screen, and I would like to thank you very much for the invitation to present our work on this session. And I hope all of you enjoy. So I know many of you, some of you I don't even know in person, but I hope you enjoy our presentation, and I hope you get motivated to work in this area and maybe with us, hopefully with us. So I will talk a little bit about remote sensing, and I don't have a slide with the outline, but I will explain. So I will present a bit generally what we do. And after my presentation, our PhD student, João Pires, will present his work. I will see on fuel lines detection, and as you will see, and we will finish with my colleague André Mora that will present Forester project. That is a project, we have several projects in this area, and this is a project in collaboration, like the other projects, with other areas of the department. So I hope you will find it interesting. So I will begin with satellite image processing. That is mainly what we do, and I will present, for those who are not aware, the Copernicus constellation. So as you probably know, there are several satellites that belong to ESA that are flying over our planet and taking pictures and sensing signals from our planet. And all this data is available to the general public. And in fact, we work mainly with the Copernicus Sentinel-2 satellites, that are two satellites, Sentinel-2A and Sentinel-2B, that were launched on 2015 and 2017. And they provide to the general public high-resolution optical imagery for land services. So these images are available to everyone, and they can be used for vegetation analysis and soil and water cover and inland waterways and so on. Okay, so that's mainly the data that we deal with, and our projects are quite not only but mainly focused on the data from Sentinel-2. And this satellite is especially interesting because it has a revisit time of 5 days. So it means that we have new images about our country each 5 days. Okay, so of course, when we talk about satellite images, as we will see, satellite images have a problem, that are the clouds. When there are clouds, the images are not that nice. But since we have images every 5 days, it's not difficult to get very frequent images of all the country, and they can be of very interesting. Its analysis can be very interesting and provide very useful information. Okay, so these images from the Sentinel satellites are available on a Portuguese portal that is IP Sentinel. That is a portal that is for public access to all the imagery from the Sentinel satellites. that's where we get our images mainly from, because they are also accessible from other platforms from ESA. But this IP Sentinel is a Portuguese portal dedicated to these images. And on Sentinel-2, we have 12 bands. Okay, so it's multispectral images. And just to give an idea, we have 12 bands. 3 of these bands are the typical RGB bands, so it's the visible spectrum. But then we have other 9 bands that can be used. So near infrared bands, shortwave infrared bands, and ultra blue bands. And these bands provide additional information to the RGB, that is information that we are not used to observe, but when we start doing it, we find very interesting, we can find there very interesting information for many applications. And that's why we work with this, and everyone almost works with all these 12 bands, depending on the applications. Some of the bands have high resolution. So the visible bands have a 10 meters resolution. 10 meters resolution, it means that each pixel has information about, corresponds to 10 meters on the soil, okay, on the ground. The other bands have a low resolution, like the near infrared bands that have 20 meters, P8 has 10 meters also, and some other bands, shortwave infrared, have 60 meters. So the different images have different resolutions, as you can see, from the 10 meters by pixel to up to the 60 meters by pixel. And usually what we do is to transform everyone down to 10 meters per pixel. That is the highest resolution, okay? And what we do with this? So with these 12 bands, we have several types of classification, and usually we have the problem of the clouds. So the Sentinel products, that is, and we call a product an image that comes from raw images, but is already processed. So the Sentinel imagery already provides information about the clouds, for example, that, as I will show, is not exactly the best information about clouds, but is okay. It is some information about clouds, and it has already some classification that usually we try to improve and not use this classification that is coming directly from the satellite portal, but we try to improve that. Okay, so one of our works was on improving the detection of clouds. That as you can see, there are on the Sentinel products several classification of clouds. They classify it on high probability, medium probability, and cloud shadows, and also thin cirrus clouds. And we put it all together, and we detect the clouds, and this way we build a cloud mask image that is used to avoid the clouds and do not consider the images with the clouds. And after that, we classify different kinds of objects on the ground. And one of our works is on water detection. So what we do with this, we try to detect all the water that can be seen from the sky, and try to evaluate the amount of water on the ground. Also, Sentinel-2 already gives some information about the water on the soil, and Sentinel-2 water detection is on your left. As if you compare with the blue areas that were marked by our software, you can see that we have a lot more areas, like, for example, here, that is a small dam that is in the south, that is not detected by Sentinel-2, and so on. So Sentinel does provide some water detection, but with considerable failures. I don't want to say with this that Sentinel is not good. Okay, please take aware that Sentinel is classifying water for all the world. Okay, and we can specialize on our country. So and that way we, of course, we can get better results from our specific area than Sentinel does for all general application. Okay, and so we do what we consider a nice water detection. On water detection, we do not use the bands 8A and band 10 because they are not useful for water detection, and we calculate several indexes. In this area, indexes are features that are calculated based on the row bands. For example, NDVI, for example, that is band 8 minus band 4 divided by band 8 by plus band 4 and so on. So there are several indexes that are used for this kind of proposals. And based on this information, we build automatic classifiers based on decision trees and neural networks, and using these bands and these indexes calculated with these bands, using in this case a cart decision tree, we trained the cart decision tree to classify what is water and what is not water, and we did the water classification, and now the problems begin. Okay, so what are the problems here? The problems here are several. Okay, one of the problems is the size of everything that I'm talking about. So to give an idea, one image like this, sorry, one image like this is typically, this is what we call a tail, and the one image like this has 10,000 pixels by 10,000 pixels. So it means 100,000 pixels. Okay, that is 100,000. Sorry, 10,000 by 10,000 is 100 million pixels. So huge images that we must deal with. So we trained with 15 million pixels for the 12 months. 1,250,000 pixels for each mouse, and used one of the problems is the size. Okay, everything here is millions, and the other problem is the ground truth. How did we? The problem is that, okay, you want to train an algorithm and you have images, and there is somewhere there is water, and you want to train what is water and what is not water. Okay, and one of the problems is that where is really water and where is not the water, so we can train the algorithms. If you look at an image like this, okay, here the water is already marked, is already painted by on light blue. But if you don't have this water painted, it is a big problem to know where the water is. Okay, and if you wanted to do it by hand, you get crazy. Okay, so how you do it? We use the COSH, that is a land cover land use map produced by DGT, that is Direção Geral do Território, official organism that from each 3 years does a map of all Portugal with the land use of all the pieces of the soil. And now, as I will show you, that's a problem, because our ground truth, that is where is the water or where is not the water, is based on COSH, and this COSH map is quite simplified, and it has several problems. It is a huge piece of work. So I'm not saying that COSH is a huge piece of work. It's a crazy work done by hand. Okay, based on on pictures taken from airplanes and helicopters and so on. So it's a huge work that they can do it from each 3 years, no more than that. But the problem is that is one classification of the soil for each 3 years, and so everything changes. And for example, the water levels change a lot during the year, as I will show you. So one big problem here is where is the water or where is not the water, because our ground truth, if we use it and we use the COSH for ground truth, the problem is that, I will show you that later, the COSH marks water on many places that effectively each month there is not water there. Okay, and when I say water, I have that problem not only for the water but for everything else that we want to classify. So the ground truth here is a big problem. okay? So what we did, we took 3 classes from the COS map, that is ocean, wetlands, and water bodies, because everything is water, and we put it all together, and we trained the classifiers to detect automatically from the images all the types of water, let's say, okay? And here you have the problem of the ground truth. What we have here, what you can see here is in black, the water detected, and it is quite well detected. And on light blue, it is the COS ground truth. And as you can see, the ground truth is completely different from reality, okay? And why? And I don't see any other way of doing it. In fact, for those who produce the COS, I'm not saying bad things about the COS, but it is the way to produce the COS, but it's not adequate for what we want. And why? Because what they, on the COS map, what is marked as water is the maximum level of water ever. Okay, so it's I'm talking about dams in this case, and it's the maximum level of water where the water goes in the maximum level. And during the year, as you can see in October, for example, the dams are quite low. And so on this mouse, the water is quite low, and the area occupied by water is much lower, much reduced compared with what is marked on the COS. Okay, but to train the algorithms, we have to give the algorithm and say the algorithm that this is water and this is not water. So the algorithm must be very robust to noise, because it needs to distinguish what, hopefully the algorithm will distinguish, even we tell the algorithm that this is water, by all the examples where the ground, not water, is considered not water, it must understand that really, in fact, water is only this and not that, okay? And this is a big problem when we are trying to teach the algorithms, but we are very happy because the decision trees, in this case, for example, they succeed to distinguish, because they consider these pixels that on the ground truth they are water, but on reality they are not water, and they succeed to distinguish between what is really water and what is not really water, and the classification results quite good, okay? And so this is just an example to give an idea about the complexity of the classification tree, but this is done automatically, so it's not a problem. And this is the kind of accuracies that we get through the year. So what we did here was to try to train one classifier for each mouse and training all the year with that mouse. And of course, when we train with January, we classify better January than all the rest of the year. And when we train with February, we classify better than mouse than the rest of the year. But then we tried to, how about train with all the mouses and classify all the mouses? And in fact, when we try with all the mouses, we get very, very good results for all the mouses. And as you can see here, for example, when we train in September, for example, it's especially bad for the rest of the year, because as I will show you, September is a very dry mouse, okay? So if we train with a dry mouse, it cannot classify green mouses, okay? Because after September, October, November, everything is much more green because it rains. And so if we train with September, especially bad for the rest of the years. And there are several months. Some of the months are especially bad for training. But if we train with some information from all the months and we test it with all the months, the results are quite nice. And this is just to give an idea about the differences between all the months. So people that believes that a picture from the sky is a picture from the sky is always the same. You can see, for example, September, October, November is this was 2019, of course, but sorry, this is July, this is August, this is September. September is much more brown than, for example, January. January is very green, okay? And we must classify, hopefully we classify the same thing, even if it is green or brown, independently, it should be, the classification should be the same, okay? And so this is the result of the water detection for 2019. This is on January, just to give you an idea. So in January, there is a lot of water, and all this, it looks noise, but it is not noise, okay? We verified most of this by looking very deep on the images, and all these small points of water are effectively there, okay? And as you can see, there are a lot of changes during the year. You see how the water disappears, okay? Even here on the river, the water almost disappears, okay? So this is March, April, May, June, July, August, September. September is the driest month in the year, okay? And in September, there is almost very few water just on the dams and so on. October, and then November it starts raining again, and December, okay? This is the evolution of a dam, okay? And when you see these kind of things, it looks like noise, but then you check it closely. This image is from Google Maps. That is a completely different technology from satellite, okay? So on the images from Google, we can check precisely what is there, and we check there, and it really is water. It's a small reservoir of water, and even this pixel, it looks like a pixel. It's not just a pixel, it's also water. And here is the way out of the dam, and it's also water. So the classification is quite good and quite sensitive. Even here is not noise, it's also true that is there, and so on, okay? But for those who are thinking that, okay, water is easy, water is always water, well, as you can see, water is not exactly always water, okay? So you can see here the differences on water, okay, depending on the light, on the wind. The wind is very important, okay? So it's not that, I wouldn't say not that easy, but it's not that straightforward that to say that water is always water, okay? And this is the evolution of the dam during the year. You can see the water levels are going up and low. And so to test what we do, we evaluated is not an evaluation of the quantity of water, but it is the evaluation of the area of water. And we compare the area of water with the official data from the dams. And as you can see, the area is very highly correlated with the official data of the water volume on the dams. What to a certain point certifies that what we are doing is quite correct, okay? Future work immediately on this area is to get the elevation model of the dams and to calculate the volume. So to go from the area up to the volume. And then what is the goal of this? The goal of this is to be able to evaluate all the water that is available in the country on the different places. And this can be important for water management. It can be important, for example, for firefighting, okay? But we don't do only water. We do, in fact, or we try to do land cover land use maps. What are land cover land use maps? Is to do what we do with water, but with several classes, okay? And with several classes, this thing becomes more complicated. And we've been working with 5, 6, 7 classes, different classes. That is mainly, for example, in this work that was done by Clarice, the student of master student. What we did was to classify agriculture, forest, barrowland, water, and urban areas. Okay, so 5 classes. Once again, the ground truth is from the COS map that have all the problems I told you about. Clarice have chosen the best indexes for classifying each class of ground cover, and did an hierarchical classifier that is one specialized classifier for each class, and then one classifier that merges the results of the 5 classifiers on a final decision for the result. And what we get, okay, this is some data about this. So to give you an idea about the size, the training was done with 120 million pixels, okay? As you can see, there are classes that the training set is typically very imbalanced. That is another problem that we have, because for example, barrowland is very rare. So there are very small areas and rare areas of bare land. And so compared with agriculture or forest, it's almost nothing. So almost any classifier will just forget bare land, because bare land is so rare that is just there for error, okay? And so many classifiers just deny to classify bare land. This is one of the problems. The imbalance of the training set, and even the water is just 15 million compared to 58 of forest or 42 of agriculture, and urban area only 3 million. Okay, so the training set is quite imbalanced. That is a big problem. And here you have the result with the 5 classes. So this is the RGB image. This is an area in Alentejo, the south of Portugal. This is a village. This is a dam, so with water, and agriculture and forest. That is not, the forest here is a very sparse forest. On the course map, the official course map, they have here as urban, that is the village. They have here agriculture, and they have here urban because it's a road, okay, and the forest. Okay, this is very much simplified. Okay, this is quite simplified, but if you do by hand for all the country, this is already very important work, very, very detailed work. But in fact, compared with the 10 meters by 10 meters of the pixel, it's very simplified. Here, I know this area. That's why we work on this area, because I know quite well this area, and I see no reason for this to be urban. Okay, it is on the course map as urban. I know the place, and there is no reason for this to be urban. But okay, it is once again the ground truth problem, and this is the automatic classification. Okay, and on some aspects, the automatic classification, I can tell you that is better than the core. For example, in this area, because it's much better here than here. This is a water reservoir. It's a kind of a small lake close to the dam that I know, and it is there. Okay, so this is correct. But for example, our urban classification is missing a lot. Okay, so this is too much urban, but this is too few. So it's not perfect. About the forest versus agriculture is not bad. Okay, is not bad, because in fact, to say that this is forest and this is agriculture is also not correct. So the result is quite acceptable. That you can do. And then after this classification that is based on intelligent classifiers, we are now doing what we call morphological processing. And what is morphological processing is to try to clean the classification image. This is an example of a classification image with the several classes, and we try to clean morphological this image. For example, eliminate, and this is just what I will show, is eliminate the isolated pixels that you can see here, that in fact there are a lot of them. They are now in blue. So all these pixels are pixels from one class different from all its neighbors, and by a simple mode filter, simple morphological mode filter, we clean these pixels, and the classification is significantly improved. Okay, however, we must be careful with this, because for example, for the urban areas, this is not that clear, because urban areas, because our classification is sparse, we are in risk of cleaning all the urban, so it must be done carefully. But morphological processing is a posh classification, posh processing that can improve the results. Okay, so to finish my presentation, that I hope gave you some idea about what you do, and my colleagues will follow me presenting more specific applications of this. I have here some research questions that I would like to launch immediately for later discussion, if possible. So some problems that we have. So the first problem is how can we find an adequate ground truth for training and evaluation? Okay, take into account that one tile of image is 100 million pixels. Okay, so if you think about classify those pixels by hand to say exactly what is there, and to get a very clean ground truth, that is not feasible, okay? Because you have no way of classifying by hand 100 million pixels and be sure that what you are doing. Okay, so that's extremely, it's crazy. So we have that problem. Everyone has that problem. So it's a big problem, and there are some scientific approaches to try to solve this, like reinforcement learning and other approaches that try to minimize the problem. But okay, this is an open question. Another open question is the temporal dynamics of land use. Everything changes from month to month. How can we take that into account for the classification? How can we incorporate texture analysis on land cover classification? Texture analysis is important. We know that, okay? How can we apply texture analysis, and what results can we? That's very interesting area, because if you look pixel by pixel, or the color, or whatever, the reflectancy that is on each pixel, that's not enough, because one isolated pixel is okay, that has information, but it should be taken into account its neighbors and neighbors of the neighbors, and so parts of the image, not isolated pixels, for texture analysis, and that can be important. Which are the best indices for land cover classification, if they are? Because there is also some discussion on the scientific area if the indices are good. Okay, many people is saying beautiful things about the indices, then we go on the results and they are not that nice, and so there is some discussion about if our indices the ideal or not. How can we relate land cover with land use? And land cover is when you take a picture is what is there. Land use is what you are doing with the land. So the difference is that, for example, a cornfield, a cornfield, and some months of the year just as soil, nothing else, and then they plant, and the vegetation grows, and so land use is what we do with land. Land cover is what is there. Okay, and when you see a picture of 1 month, you can know sometimes you can, other time, in other situations, you can have no idea about what the use of the land is that is there. Okay, you just, if you are successful, you just can know what is there, not what they are using the land for. Spatial clustering is another area that shows to be promising for land use classification, and also on open field, and the morphological image processing that promises classification enhancement can also be interesting to explore. So these are some research questions, let's say, that I would like to raise here, and okay, we see later after the other presentations what you think about it. Okay, so from my part, for the moment, thank you very much, and I give now the floor. So just before I finish, some acknowledgements to all the people that is working this area with us, and so there is a list. I'm very, very deeply sorry if I missed someone. I hope I didn't. The order is non-significant, is at random. Okay, so many thanks to all these colleagues and students that work with us in this area, and so I give now the floor to João Pires for the fuel brakes that will present what is doing on fuel brake maintenance detection. Okay, so thank you very much. João, is up to you now.
Okay, good afternoon. I'm going to share my screen. I'm in two accounts because my computer don't have microphones, so I'm using the microphone of my computer and of my mobile phone, and sharing the screen from my computer. I'm gonna start the presentation. Okay, so I'm going to present about what we are doing in the project Full Moon, that is regarding the semi-automatic full brake maintenance operations detection. As introduction, I would like to talk about the wildfires that are one of the most destructive natural disasters that they can lead to damage in the economy, in the ecosystems, and can lead to also to human casualties. Wildfires are common not only in Portugal, but in the US, Canada, Mediterranean, Europe, and southern Australia. And because of that, the Portuguese authorities implemented a full break network, being it a proactive strategy to prevent and help in the fight of a wildfire. The network has 100,000 and 125 kilometers, but only the most priority areas are already implemented. You can see in the map what is the plan to implement. So what are full breaks? Full breaks, as I said before, are responsible for controlling the wildfire and create strategic positions for the firefighting, also to create road networks for the firefighting cars can pass and to deal better with the fires, and also and they are composed, as I said, by a road network, and they have a minimum of 125 meters. Here you can see from a Google Earth image the aspect of a full break. We have vegetation, we have a strong cut, and after you have a vegetation. So the full treatment, a full break only is effective if its quality is assured, and if it was correctly implemented. Nowadays, to understand if the full treatment was correctly applied to a full break, it is done by ground observation and by observing satellite imagery one by one. After, for example, here you have the example of a full treatment. We have here the image before the treatment and after the treatment, and you can see this is a true color image. It is you can see this it's really easy to see. And the ICNF is the entity, the Instituto de Conservação da Natureza. It is the entity responsible for monitoring these operations, to schedule these operations, and these operations normally are.
João, não sei se estás a ouvir, mas deixámos de te ouvir. Quer dizer, não fui só eu que deixei de ouvir.
Sim, também deixei de ouvir.
That's why to verify. Are you hearing me now? Listening to me?
Yeah. João, desculpa. Estavas no ICNF, pá. Não ouvimos mais nada.
Okay. So ICNF, as I said, is the entity responsible for scheduling the full treatments on the full breaks, assuring that they are correctly maintained and that they will be effective when a wildfire is ongoing, or in preventing that the wildfires. The goal of our work was to monitor the full breaks. We use the full breaks shape files, the ones that I presented on the first slides, that shows us where they are, the full breaks delimited geographically, Sentinel-2 imagery, and a detection method. And our output was the treatment months, to know if a treatment that was contracted to a third party occurred or not. As said in the previous presentation, Sentinel-2 has a 5 days revisiting period, a resolution up to 10 meters, and 13 spectral bands. Although there are 5 days, as said before, most of the times we don't have image each 5 days because of the atmospheric conditions. Sentinel-2 also, the image may have geolocation errors up to 15 meters that we dealt with in our methodology. Presenting the study areas and the data. Here in the map you can see that there are many places from Portugal, from north to south, and many types of land cover. We have cocoa, eucalyptus, pine forest, shrubs, bush areas, agriculture, and artificialized lands. This is important. Why? Because normally remote sensing methodologies or works only focus on or one type of land coverage or one specific regions. We try to develop a method that work in all the area of Portugal. So we wanted to achieve a generic method instead of a specific method for each region. We used from there the spectral bands and also spectral indices that are derived from the spectral bands. Our tools were fundamental quantum GIS. Quantum GIS is a geographic information system that already have a lot of libraries tools to work in this field, and also because it's one of the tools that ICNF uses, and our final tool is being developed, but already have most of the functionalities implemented, is a QGIS plugin that is responsible for detecting the full treatments and also to estimate the vegetation recovery after a full treatment to sectional to help the ICNF sectioning the full breaks. Also, it has running on the back a Portuguese database to store all the data. The other tool was Google Earth Engine that was used also to not detect the treatments in the full breaks, but to generate full treatments maps, coverage maps, to understand in all Portugal, in all the network, where may have happened some changes or not. All the tasks that are implemented in Google Earth Engine are being implemented in Quantum GIS to have a unique platform to work, and that we chose Quantum GIS because of what ICNF wanted. So our outputs are the full treatment maps, the full treatment detection, and the full break vegetation recovery estimation. Beginning with the full treatments, we had two methodologies. Both of them use the Sentinel-2, the full break shape files, and the detection map, having as output the months of operations. They can work alone, but the information is complementary. The full treatment detection is an object-based methodology. An object is a group of pixels. Is the spatial analysis instead of looking just for one pixel. This method detects full treatments if they occurred or not within a linear shaped file, but they don't give information about the coverage of the treatments. Although the full treatments that only occurred on 50% or up to 75% of the full break are not detected, giving the information that the treatment was a bad treatment in the full break that should be done again or something else. The pixel-based, the generation of full treatment maps is a pixel-based approach where the full break status can be assessed. It neglects the spatial information, but there were applied some post-processing techniques to help this problem. The output of these full treatment maps are maps of the full network with the pixel signal, with the pixel data, where being the pixels corresponding to the date of the where the month of operation occurred. So now, beginning with the full treatments detection, we have three stages: the image preprocessing, the time series generation, and the operations detection. In the image preprocessing, we start with geolocation correction. As I said before, there is a 50 meters of geolocation errors that may occur. And since we are dealing with full breaks that sometimes may not be big areas, they can these offset can decrease the quality of the prediction. After that, we equipped our areas of interest, and after that we compute the object value. We use the mean value as the object metric. This is an example of photo cruise. We have this image, we cut the area of interest, and after we have the mean value of the region for the reflectance bands. Next, the time series and generation. We generate from the object the values for each month, and after for each month, no, for each observation, and after we have a noise filtering where we apply it for comparison a mean and a median filter. Here in this graph we have in green, which is the time series considering all the observations, is very noisy. In yellow we have the median filter, and in brown the mean filter. They both smooth the data. But as you can see, the mean filter smooths more the data, which may be better for avoiding more false positives, wrong detections of treatments. The spectral readings were computed by in quantum G's. We don't get the image from other source. We computed ourselves the image, and other of that we computed the values from the mean values obtained for each month instead of generating indices image. We compare the methods and they give really similar results. So since it's faster to compute it from the mean values, we use that approach. After the operation detection, we used artificial neural network to detect the operations, the amount of the treatments. But before we did several feature selection to understand which were the best features to solve our problem, and the best features were band 5, excess of green and excess of red. This is interesting, especially the part of band 5, because band 5 is a red edge band that was implemented on Sentinel-2. Sentinel-2 specifically to study the vegetation. For example, in a Landsat mission, that is a similar mission from NASA, they don't have these bands, and it's interesting to see that in our problem they have had a good importance. Here you can see that we did the steps that you take to select the features, the Pearson's correlations, the select k-best, that is a Python algorithm, and the time series analysis. And after the structure definition of our artificial network, we tested several structures, and we ended with the structure using one hidden layer with 53 neurons. After now, I'm going to present the full treatments maps. This step was developed by ISA, Instituto Superior de Agronomia, one of our partners, but the steps are almost the same. They began with the image preprocessing, after the mount compositing, where they do the mount composites, and after supervised classification. They also do the geolocation correction, but they use different algorithms. They use the cloud masking algorithm sent to core, that is from ISA, an algorithm to mask the clouds and shadows and avoid them. And they also generate a time series. Here you have an example of a time series. This is pixels time series, not object time series. And for example, here is where maintenance operation or full treatment occurs. At blue is outside of the flow rate to see what was expected, if it was vegetation and if anything had happened. After they did the composites, they did, and it was done NDVI, maximum NDVI composites, and also they selected the time step of 1 month because it was considered a good trade-off between the phenology variations and also because of the number of available images. So this is the example of the image. Here we have the flow break before the NDV values of the flow break. Note that we have the flow break and also the vegetation, the surrounding vegetation to compare it. And here we have the composites difference. The operation was in May of 2017, and at red you can see that the difference is greater than the difference on the borders. So that means that we had the operation. So as I said before, for the classification to improve the results, because they don't add spatial information for spatial information, because they use pixels, they applied some methods as the erosion and double opening, which improved the classification. So it was a way that it was found to get the spatial information into the problem. Now I'm going to present the results. First, we have the results for the full treatment detection, the object-based method, where we have the overall results were good. As it was predicted, the mean filter was better when avoiding false positives. You can see that because of the greater precision, and but it also detects less operation full treatments, and we can see that because watching the recall values. Also, regarding the full treatment maps, the pixel based detection, the results were also good. We can see that the double opening was the best approach. The double opening is the post-processing method that one of the post-processing methods that they use. But the results are really similar between the object approach and the pixel approach. After, in 2020, we applied both methodologies to the current year, to the data of the current year, and we have the results that within 35 full treatments, only 4 were not detected, and this data was not using in the training. It was just testing. It's like on-field testing. After regarding the resulting information, as I said, the object approach focuses on the full treatment date, and the pixel approach focuses on the coverage date. Here we have an example of a full treatment map. This is from Serra Candeeiros, one of the flow breaks, and we can see clear when the operations occur and the coverage of them. For example, here we see that some of the parts may not have been operated, and others, this one have a lot operation that was better. But although the object-based approach don't give the insight of the quality of the treatment, it is prepared to avoid detecting treatments that don't meet some degree of quality. We tested, for example, for when the covered area by the full treatment was between 0% and 25%, more than 25%, and from 3 cases there was 0 wrong detection. Between 55 and 50%, 25 and 50% from the for number of cases. There were again no wrong detections. Between 50 and 75%, we just had two cases and one was a wrong detection. But we can say that now, if the treatment don't have a 75 more than 75% of coverage, it won't be detected, but by our algorithm in the majority of the cases. After that, we begin studying the estimating the vegetation recovery. This part is important. Why? Because after full treatment, the vegetation starts growing, and it is really important to understand when we need to operate the full effectiveness. So, are you listening to me?
Yes. Yes.
Now, yes.
Now, yes. Yes.
Okay, sorry. So, what we wanted to do was a relative estimation of the vegetation recovery in a flow break after the treatment, based on the NDV temporal time series. Again, with resource to the same sources of information. Sentinel-2 flow break shape files, and we developed an estimator for that, which gives us the relative vegetation recovery. We wanted something that was an easy and understandable tool for assessing the full break state, and help the ICNR scheduling the full treatments. Which are the pros and cons from this methodology, especially the fact of being a relative estimation? The pros is because it adapts to the flow break. Sometimes, when I say this adaptation, is not only in terms of different characteristics of the flow break, type of vegetation, if it's a mixed vegetation, type of climate, or a lot of things, external factors that can matter, but also if it is a flow break that is being periodically treated, or is it a flow break that don't have yet a periodically treatments. So if it is the vegetation is saturated, or if the vegetation is being cut before the saturation. Also, it is robust to the phenology, that the phenology noise in this change in remote sensing in general normally is a really bad thing, because it do not help to develop single classifiers or single estimators or detectors for many areas. And also, it was important that it worked for all portable. We tested a lot of some areas, and it worked for the majority of them. The cons is because it works of an absolute metrics, like the above ground biomass or the forest tech, that they are metrics that normally in forest studies are very important. And also because it is also an object-based method, it needs well-defined shapes. If we define a shape where the treatment occurs in just part of it, and not in the full object, in the full shape, the estimation will start decreasing its quality. Here I'm going to present the method. Here we have image of several images from Fundão. The first one was in 2017, before the full treatment. Next is after the full treatment, right after the full treatment. This one is 2 years after the treatment. This one is 3 years after the treatment. If we compare the first and the last image, we can say that they are pretty similar. So probably this is already time to operate the full break again. Here we have NDVI time series. As you see, we can see the trend of growing vegetation growing, but the vegetation growth, but also we see these decreasing values, and after increasing values again. This is due phenology in the year, especially In the second year, we see most. Phenology noise is very bad for these scenarios. We can have the trend, but it may be hard to understand, okay, comparing to the beginning, how much it is now. So we developed a method based on the interannual difference to estimate the vegetation growth that occurred in a month. And we compute that for every month, and after in the final we have a final value of the estimation. One of the good things also of the method is because it gives us month estimations. Also, we define a reference systems that the reference comes from the NDVI time series. For example, for the maximum value that for the maximum reference, use the maximum value from the NDV values before the operations, and the minimum reference is the point right before the NDV starts growing. This reference system is what allows the method to apply to different flow rates in different areas with multiple external conditions. Again, we have the same image. It will help us to see how now our result from Fundão, where in this our image from Fundão, we have here the estimation, the estimation of the full break state, where we have results that are really more easy to understand, and they seem to be more according to the reality. This is in the x-axis we have the months after the treatment, and we see that after more or less nearly 3 years is when the flow break starts to reach the state previous to the full treatment. It was expected when we talk with this and the ICNF. Normally this is appeared, and this is very useful tool for them to understand how the state of full break is. Here we have other results, and as you see, all the results seem to be well behaved and to represent the reality, because one of the first things that we see is because here we don't have any phenology noise. I'm not saying that we eliminated the phenology noise, but we reduced that a lot with this method. Also, we see that was expected the slower vegetation growth over the time, and also that full breaks that are periodically treated have better estimations. As we see in blue and gray, certain Fundão are areas that are being already periodically treated, normally I think in a 2 or 3 years basis. And also another thing that was really good to observe was in the orange line of Serra dos Candeeiros, the sensitivity of the method to new treatments. For example, to understand that is not only an implementing method, in Serra dos Candeeiros, in the month 30, it occurred the treatment, not in the full break, and we start seeing that the value starts decreasing.
Sorry, conclusions. Sorry, just because you were a bit.
Okay, sorry.
Bit like
conclusions. Yeah. So, in the pre-processing stage, we need to understand which are those observations because of the atmospheric conditions. We need to correct the geolocation. That is more important in the at the pixel approach than the object. In the data sets, we need to have n-match shapes for the object approximation. And again, as one of the questions from the previous presentation, we need to have reliable data. It is important to have good ground truth data for the estimation or the detection. And both methodologies complement each other. We get the coverage of the full treatment from the pixel approach. We get the full treatment states from the object approach. Also, but both methodologies evidence ability to solving the problems by itself and alone. Finally, the future work We intend to increase the number of observations, of observations, especially by recovering from quality data. One of the things that we can do is using SAR observations, SAR images or other images taken from Sentinel-1, and merge both methodologies. So we want to increase the usable data. Also use SAR data to understand if they can give more knowledge about the vegetation recovery and may progress for more precise metrics like the above ground biomass and the forest height. Also improve the forest state full break estimations and fusing more types of data, especially SAR, as I said before, but also wider data that nowadays is becoming more available. Sorry, we have already these published papers, if you want to see, and the United College Fundação para as Ciências e Tecnologias. And thank you for your attentions. I don't know if you have any questions, comments, or suggestions, maybe after the next presentation.
Okay, I think I will start my presentation. So let me just take out here. Okay, so you are seeing my screen, I hope.
Yes, we see.
Yes. Okay.
Yeah.
Thanks. So, so my name is André Mora. I'm working also in the group, in this remote sensing group, and today I'm presenting here one of our projects where we are involved. It's Forester, where we apply several of these, where we use, let's say, is a project where we use these remote sensing technologies. So this is interesting in the context of the CTS, because it's a project where there is a strong collaboration between different groups. So the project is led by João Góes and Luís Oliveira, so it's a mixture. And we have people from electronics and people from computer science and also from telecommunication. We have Marco Becco also contributing in the telecommunications. Well, this project is the idea is to improve decision making during wildfire crisis. So the idea is to use technology during wildfire combat. So it's not just prevention, it's really during the wildfire. And the idea is to develop a decision support system integrating various sources of information based on the artificial intelligence, sensorial data, satellite image processing, and people from the agriculture. They use these real-time fire propagation predictions. Well, I will not go into details we are a bit tight in schedule, so I will not go into deep on the models, but just to show our consortium, we have people from hardware and software, people from cartography, so Nova, EMS, and Direção Geral do Território. They are the official, they are a public institution responsible for the cartography in national level. Instituto de Telecomunicações is helping us on image processing. We have people from Aveiro doing weather forecasts, and people from ISA, from agronomists. They are doing fire propagation modeling. So very important to prevent, to know where the fire is going to be in some minutes time, some hours, let's say, not minutes, some hours. Well, we have a very good case study where we have an end user that is Vila de Mação, the Mação municipality. They already are a very technological municipality, but because they already had a decision support system developed by them. And we collaborate here to add more functionalities and can contribute with other ideas. So they have this van that shows that has inside so this is the command of the fire, where people are sitting there with the computers and radios, and they can monitor the people in the field. Well, our main technological contributions are at hardware level. We are developing multi-sensor systems for taking data from the field to the center to the centralized decision support system. At software level, we are going to there are people working on updated land cover, land use maps using artificial intelligence, fire propagation models, improved resolution satellite images. So this is one of our tasks in our group. Decision support systems that integrate advanced visualization and multi-source data fusion. So this last two is where our remote sensing group is working. So some of the contributions I will present here, some of the contributions that the project already produced. So one is vehicle protection and thermal mapping. So here we want to protect the vehicles and the people that are the firefighters. Developed technology that can do early warnings of situations that they can be involved in. So, and in this case, we are developed a thermal sensor with 360 degrees the field of view to detect heat spots around the vehicle. Can be detected, or if the vehicle is already on the fire front, probably it will always flash. But we also said that we can use this for detect heat spots like reignition spots and things like that. So this could be useful. The model also is equipped with GPS to locate where is the vehicle and so on, and have also other type of sensors. In this case, we used oxygen concentration sensors inside and outside the vehicle to detect dangerous situations as low oxygen concentration in the proximity of fires. This is a real problem because the machines that are operating near the fire front, even the machine, not only the operator, can feel dizzy with the lack of oxygen, but also the vehicle can stop without the oxygen. So that's something that is quite important for to avoid dangerous situations. Other contribution is an app, M-Forest app, where the idea is to have a mobile interface for people that is on the field to read the sensors from the vehicle and communicate them to the centralized decision support system that can be used for monitoring as well, for the firefighter commander to see what is happening, have like a mobile interface for the decision support system. And for other actors as well. I will not go into details, otherwise I will lose my time. Regarding the remote sensing, this part is more interesting. Here we present here the super resolution satellite imagery. So the idea is that Sentinel-2, the satellite we are using along our works, has 10-meter spatial resolution that can be insufficient to detect smaller infrastructures, as, for example, detect if the road is blocked by some trees or if it is open or not. And for that, a sub-pixel analysis, like dividing, having not 10 meters per pixel, but less than that, could be useful to see beyond the 10 meters. So, and detect things like, we have here, for example, a low resolution image on the top, and this is low resolution. This is a Sentinel-2 image, and have here a higher resolution image. This is not obtained directly from our software. Let's just disclaimer, it's another work, but they can, from the previous image, they can get a higher resolution one. So based on previous information. Well, in our case, we developed an algorithm that takes the opportunity of the revisit time of the 5-day revisit time of the Sentinel-2, and there is a geolocalization error of 1.5, maximum geolocalization of 1.5 pixels. So the idea is that this spatial shift can also be improved, can also be used to improve the spatial resolution. So the idea is that the satellites, they are quite good. I would say that to locate and geolocate the images, although there is always some minor error that, for example, one specific place, a house, it's not correctly imaged from one revisit to the other. So there are always some minor error. Maximum reported is 1.5, but usually it's around 0.5, 0.3 pixels. So, but there is always a small shift between the images. So, and the idea is that we developed an algorithm based on this information. So these two features, let's say, that uses multiple images. So in our case, we used 6 images, previous images, let's say. And basically, we want the images to be the time interval between images as short as possible. We want images to be the closest as possible. And the images should be from the same season. Otherwise, we will get things like this, because the vegetation will change too much, for example, and we get a confused pixel, let's say a subpixel where they will going to have confused information. So, okay, the images are misaligned. So this is not new. I already said this before. And for example, I will show here on the image displayed here on the right. We have 3, in this case, in this example, we have 3 images, A, B, and C. So A in blue, this is slightly shift according to B and shift also to C. So there is this difference between the images. So the pixels are these bigger squares. And we want to get, in this case, in this example, we want to get a zoom factor of 3 times. So we want to have, for each 10 meters pixel, we want to have 1/3, like 0.33 meters per pixel. So the idea is that, so to get for each of these new pixels, we want to get the k nearest pixels from these n images. So, and the idea is that, for example, for this one, we want, in this case, we studied and we found we have the analysis of this k factor, but in this case, we got for k 5 neighbor pixels. We got these 5 neighbor pixels and obtained the new one from the weighted average of these neighbor pixels. This weight is proportional to the distance that is from that pixel. Okay, so, and the idea is that we get a higher super resolution, super revolved image on this case. So we will just display here an example. This is a small video showing at your left the original Sentinel-2 image, and at your right the super resolution image. Up to now, they are more or less the same. It's slightly blurred on the right, but when we get to a zoom that is closer and closer, I will get it faster. We can see that the original one is much more pixelized, and we get, although that is slightly blurred, we can get more information from, we can at least understand more what is on the right image rather than the left one. Okay, so for example, we have here this bigger white block, and we can see that is like a rectangle or a football camp or whatever. So that is our super resolved image. The decision support system is another contribution from our group. It's a centralized multi-user portal, allows maps visualization, linked plots, upload figures and documents with geolocation to know exactly pictures from the fire front and from the any other place that it could be interesting. Display vector information on the maps like fire propagation, full breaks network, water reservoirs, census population, and things like that. We also added data visualization clustering to see more data as we zoom in and zoom out on the system. And we have a tool for temporal reproduction of the past wildfires. I will skip this slide. It's not important. I think it's more important to see this reproduction of one of 2019 fires that were actually on Mação municipality. We can see here the evolution. This evolution is taken by the people on the ground, so that they are always marking where the fire is, and where we can see here the vehicles, photos, and so on. And on our right, we can see here the clustering example. We can see that when we are zooming, we start to see more detailed information. So in this case, we have the population. When we got to zoom in, it's important to know if the fire is reaching a higher density with population or not, and we can the fire commander can decide what to do in this case. Okay, and I think this is our main contribution so far. Some of these prototypes already developed and are ready for testing on the next fire season. And just like to open some of the questions that are still open. For example, if our algorithm of super resolution can be improved with other techniques, this is something is working, it's open to discussion. GPU and FPGA processing can be used to reduce the execution time of these remote sensing techniques. It's also one of the topics that is we are also working on. Can we combine maps to have more information in one single view on those decision support system? That's something that we want to study as well. And which plots visualization techniques can be used to have more informative user interface? So the idea is that there are lots of nowadays interactive visualization techniques that can be useful, that can be useful to display lots of information in the simplified way. And this is one of the topics that we can work on this. Thank you very much. I think I don't have a final slide. I will leave this open research questions here. But thank you all for the attention.
Okay, so thank you very much for the 3 presentations. In fact, we got 3 seminars in one, but the topic, the 3 presentations could give us a very broad overview of what kind of work you are doing. That's very, very interesting. Unfortunately, we are almost out of time for the discussion period. Nevertheless, I would still give the word to Luis and Pedro if they have some question or comment, but we really have very little time now.
Okay, thank you very much. So maybe I can start the discussion. Thank you very much for your nice presentation. Regarding the last project in which we are working, I would like to highlight a key point, that is, we don't know yet with a good precision if the forest is clean or not, because we cannot see what is under the trees. So that's a limitation that we have actually with the satellite image. So I have two questions. One is for André. That do you think that in future satellites can give us some information about this? That and can allow us, for example, close to the village to identify red zones before the summer that needs to be cleaned, otherwise the people are in danger and the village are in danger. And also I would like to ask to José Barata if their drones and the LIDAR could help us in this topic to address this problem.
Okay, so first question that was directed to me. If we satellites can see below the cover tops, I don't think so. So the cover tops block almost everything. Okay, so maybe if it is not too dense, let's say the forest is not too dense, maybe we can see, can estimate what is under the, but I don't think so. The second question, sorry.
It's related with the help of
for
other sensors.
Okay,
we have already sensors in the project forest, so it helps a lot. But we still have room to add other information, critical information.
I think something that is could be interesting for the protecting the people around the rural areas could be exactly to use these techniques that we used, for example, to estimate the recovery of the forest on the Full Moon project. Something that I think it's we need to have all the areas clean around the houses, and yes, this technique could be used exactly to monitor this, and for example, for the government to say in every year to see, okay, there is we can see there is a reduction, effective reduction on the fuel loads in each municipality, for example. That means that the people is actually complying with their obligations to clean the shrubs, basically.
Luis, if you allow me, I just would like to say that I'm sorry, but the next satellites will be to check if people is at home to control the pandemic. So forget about the trees and below the trees, and they will provide new satellites just to see if people is at home. Okay. So.
Yes, I understand that. And José Barata, maybe you can add some comments on this.
You need sound, José.
I am trying to reduce, and even without camera, I was, because I'm full of cuts. You're talking about the use of LIDAR for the vegetation below the canopies?
Yes.
This is what you were talking about?
Yes, yes, yes.
So this is some I would say research challenge, because many things the LIDAR can get from the canopies, but if you have very dense canopies, forget that you cannot get it, what is behind. Although with some resolution, if, for instance, pine trees, in fact, are not very, very dense, and you can extract some at least to get an idea of the bushes. That is what you, but this is a special work that we need to do, that's definitely.
Because that could help us a lot in fire predictions. So we have an ignition in this point. We need to know the fuel in the area. And sometimes you only know if it's the type of trees that are there, not the amount of fuel.
And Luis, I can tell you that, for example, in Amazonia, in Brazil, they have that problem because the people is removing the trees, one here, another there. So satellites cannot detect if they don't remove all the trees, they remove just some trees, because the satellites don't go inside below the trees. They remove some of them, and the satellites there is, so far as I know, no solution for that. So it's quite difficult to see, let's say, below the trees canopies.
Does you can, if you are a lower altitude, you can. But
yeah.
Yes, the advantage
From
is
the
that
high,
you have the drones. We are at lower altitude. At least with satellite image, we can identify the risk zones. Of course, we don't have resources to cover all the country with LiDAR, but maybe in some critical points they could help us. And I think that a very important research area.
Flights for specifically for certain areas with fixed wing drones is the only possibility I see.
It's time to open the floor to the audience, to our colleagues, to put some questions if they want. I can't see you all, but for sure you have some questions in your mind. Anyone?
well, at least now everyone, I think almost everyone knew already, but now you can be sure that Big Brother is really watching you. So that's for sure. We can know almost anything from the sky.
I have one or two questions.
Yeah.
One a little bit technical, the other one more general. But my first comment is to André, because I really hope that you won't be able to test your prototypes this summer or next one. It will be for a good reason. That means that the fires will be quite a few and you won't be able to test it. But my question is the first one. We saw here two different applications, water, full brakes, and fires. My question is if these three applications have a common basis. I mean, all of you are getting the image from Sentinel, but then the training approach, the classifiers are common to all the applications, or you need to adapt these technologies to the application?
Well, I would say that we do a lot of the first project of water. It's not just water; it's land cover, land use maps. So it's José showed the water example, and the other that is classifying lots of types of terrain. Maybe José can say more for that, but yeah. I think we use different techniques to explore different techniques, but we don't reuse from the three projects. We don't reuse that much because different applications.
Theoretically, you could use exactly the same techniques. The question is that, in fact, when you start working with it, you realize that if in some areas some techniques work a little better than the others, so then you move to those techniques, because you can say, for example, we can use let's say decision trees or neural networks for everything, and it would work. The question is that on some areas, the neural networks have some advantages, and the others, the decision trees have another advantages, and so depending on the problem, you end up using different techniques because for some reason they have some advantages. For example, decision trees, you can read it and you can try to understand it. Neural networks, you don't understand anything; they just work and you don't know how. And so, if you want to understand something, it's better than decision trees. But if you are just looking on the performance, maybe neural networks are better. So it depends on what you want. Theoretically, you can use the same for everything, but in practice, you end up using different techniques.
But for example, you said the decision trees, but there is the random forests.
Random forests.
And random forests, they are decision trees, but they are not so readable because there are so many. It's not so readable as the others. Okay.
Can I add something? Are you hearing me?
Yeah.
Yes.
I just want to add because the first presentation about the land coverage is more about the classification, because in remote sensing we have normally not only in vegetation remote sensing or forest remote sensing we have two fields: the change detection, what was done in the flow rate monitoring, where normally we generate time series, temporal time series for understanding the difference that occurred. And we have the land classification that was in the first presentation, that normally they don't need time series, and there is a difference that implies that okay, regarding the classification method or the regression, we can use the same, but the basis is normally different.
Okay. So my second question is, if you are working close with some Portuguese authorities, not only to firefights, but to create a strategy in a medium, long term to plan the growth of urban areas, to protect natural resource, these kind of things.
That's the goal of DGT, Direção Geral do Território. That's their goal, and that's why they produce the COS map, and they are now starting to produce the COS SIM map that will be updated every year, and with changes, monthly changes. So the idea is to provide all the public administration better tools for land administration. So that's the final idea, is to provide to all the public and private entities better information about the territory. And you cannot, the images are not enough, because people, it's impossible to understand the pictures. If you give just the pictures from the satellite, it's impossible to understand what is there. So you need classification so people can evaluate if the pine trees are growing or reducing the area, or eucalyptus, or where is the urban areas, if are they growing or shrinking, and so on. So all that information. And for example, for the water management, what is the, André, APA, Associação Portuguesa da Água, algo assim. Não, Agência Portuguesa do Ambiente, Agência Portuguesa do Ambiente, sim, so for water management, they are also very interested to know where is water and how much water is on each place, and so on. So there are several, the ECNF for the forest management also. So there are several entities, for example, in IPSTER's project that I'm coordinating. We have a scientific advisory board where all those entities are there to observe the results of the project, and to hopefully to get some profits from the project. For example, for forest management, water management, and also for agriculture, because they want, for example, on agriculture, there are lands that are allowed to make to use the water, and sometimes they give the permission to some people that then don't use the water. Okay, so they get the allowance, but they don't use it, and so they want to be aware of which lands are really being used, and they cannot visit with a car visiting everything. So they need satellite images that tell, okay, this area is being used during the summer, the water is being used, and it's okay, they are taking profits of the land or not, and so they can change that allowance to other people, and so on. So there are several applications that, and they are aware of that. So they are already aware, and they know that these applications can be useful for them.
Okay, I think it's too late now, because we are out of time compared to what was the planned schedule. So I think we have to stop here. So once again, I would like to thank all the presenters and also the attendants for this very interesting session. I think this was a very good opportunity to know more about a very interesting research area in our center. And this was really a great opportunity to see what's going on in detail. So thank you very much. And the next seminar in this series will be on the 14th of April. So the topic will be about cyber-physical systems contributions to green and comfortable buildings. And the presenter will be Daniel Eldenay. So you all are welcome to the next session. And now I would like just to finish wishing you very nice holidays and a happy Easter.
Thank you very much, Camarinha. And if you allow me just to say that if any of you is wants to work with big images and nice image from the land, we are open to any collaboration. So we have lots of images, and there are lots of images, and we have lots of problems. So you are very welcome. Thank you very much for your attention. Hope to see you next in 15 days, in 2 weeks. And nice Easter for everyone.
Bye.
Thank you. Bye.
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 Bye. Thank you.